a very like kind of like I don't know yucky day.
I mean, it is raining. I
I
like
like
rain.
rain.
I like opening
I
up all
love
the
rain.
windows. Once y'all leave at the end of the day, I open up all the windows because I like to see it.
Smell the wet
Here.
grass. I can smell
I like it.
Rain is so good.
Alright, I gotta. Alright, what can be described as a periodic back and forth motion that transmits energy?
Let's start with
Starts with W.
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 Waving. Oh wait.
Wave. Alright, good stuff.
23.
Alright, what do you call the top of a wave?
Chris.
Good job.
15. Crescent moon.
Oh, what do you call the bottom of a wave? Ethan's turn.
Let's start with
T.
Trop.
Drop.
7.
Alright, what do you call the distance between any two corresponding
Wavelength.
points? Yep, on successive waves.
26.
Also, sorry.
Uh,
Alright, what do you call the waves like height or the strength? It's from the middle up to the top or the middle to the bottom.
Let's start with
A.
amplitude.
Amplitude.
How do we fix that?
What? I can move it, but I can't move the sound. Like it's embedded in it, and I don't want to accidentally mess up the game by trying to go in.
you really do that, don't you?
What is it?
You really do want to mess up.
I could not hear quick.
5.
You said
Five.
5.
Very
I
quiet.
couldn't hear because other people were talking.
He's also
That's
I
Chris.
know, I can barely hear it too.
Alright,
Yeah,
what
Chris.
is what's the symbol for our wavelength? It's the like the weird upside down Y. What do you call that?
Let's start with
L. The Greek letter.
lambda.
Get up.
I guessed that.
Good.
Lindonia.
19.
19. I cannot. It bothers me how they start at the bottom and go upwards. I always want to go to the top and go down. Alright, what is the number of complete waves that pass a point at a given time?
Say it again?
What do you call the number?
Frequency.
Yep, frequency.
It's 11.
Alright, what's the SI unit of frequency? H. Guy's last name.
Hertz.
Hertz.
Is it Hertz?
Alright, what do you call the rate at which a wave travels?
Start with
S.
speed.
Yep, just speed.
What in the world? I'm just guessing.
Good job, Ethan.
16.
Alright, alright, if you increase the wavelength and you keep the speed the same, will the frequency increase as well or decrease?
Say it again?
If I increase the wavelength and I keep the speed the same, will the frequency also increase or decrease? Decrease, so they're inversely proportional.
28.
17. 30.
Let's see. Alright, who wrote Optics?
Oh, no, I didn't.
Sir Isaac Newton. Alright, who came up with the wave theory of light?
Christian Lockenfeld.
H.
Hayden? No. Hayden?
What?
Hayden?
I'll take that. Huygens.
Hydra.
Huygens.
Autobots. I can't remember what our last number we had on the last one.
Junior high played this a lot, so I moved around quite a bit.
1.
Alright, who came up with the particle theory of light that light's made up of like BBs basically?
What's that start with?
N.
N?
N.
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 Is it, what's first one start with?
I.
Isaac Newton?
Yep.
I thought it was someone else for some reason. 29.
Alright, who came up with the electromagnetic wave? Who is this guy? His last name begins with an M. M. Alright, Chris, raise your hand and steal it. Go. Alright, Chris.
Say the question again.
Alright, who came up with the electromagnetic wave? Or came up with that explanation?
Last name starts with N.
M.
What's first one?
J.
Yeah, three. There's like 3.
Yep.
Maxwell.
Good job, James Clerk Maxwell.
33.
Do we have, oh, I think you're pointing. Yeah. Alright, let's see, what's the speed of light loosely in a vacuum? So it's Ethan's turn now. You can give a rounded number.
Oh, okay. 3.00 times 10 to the Times 80.
Good job. Meters per second. So 3.00 times 10 to the 8.
34.
Alright, I think that maybe that's as far as we got. So we'll go through and we'll let y'all each pick 2. So we'll start with Ethan and we'll go.
Oh, come on.
Well, it's my
No.
turn though, technically.
It'll go
It's
backwards
Chris's
and then
turn.
we'll go Chris and
Yeah,
go back
but you just said
again.
it's my turn.
Nope, too late. I already picked Ethan. Alright, Ethan. Pick one.
Alright, 17.
17. Alright, Quentin's turn.
27.
Alright, Chris' turn and then Chris should go again.
24.
Alright, so.
I was gonna guess that next.
Alright, go
I
ahead.
was gonna say
Turn
that.
over to
That's
page
for
94.
Kobe.
94, that's basically the last thing we talked about. So we're talking about light in this section. So here's a picture of the electromagnetic wave. I thought I had yesterday and apparently I didn't. So you have a magnetic field and an electric field. So it's the idea of they're oscillating or vibrating at right angles to each other. And again, I can't represent this very well because I have matter and so my arms can't go through each other. But it's the idea of it's going back and forth and up and down at the same time with those oscillating fields. It's on page 94. So who came up with the electromagnetic field or electromagnetic wave idea, Quentin?
James Gordon.
Maxwell. Just make a note for him as well. These are interesting because these can travel through space. Why is it good that light can travel through the vacuum of space? Because most waves, almost all of them, have to be transmitted through something, but light is the exception.
Because it couldn't travel space, you couldn't see anything. And you wouldn't be able to see the sun.
Yeah, and the sun gives us light and also gives us energy. So it's a really good thing that light can travel through to the vacuum of space because otherwise we wouldn't get our energy. What?
So technically energy. So is it the light? Is light in itself just energy?
Yep. Like that's one of the reasons as to
So
how
we're not
come.
getting energy and light, we're just getting light and that's giving us energy?
Well, light we use it to see. Like there's a bunch of different properties of light. Like your book points out on page 95 that there's different types of light or different types of the electromagnetic spectrum, as we're gonna get over into this. We only see in colors in that very narrow range. If you look on it, that visible light is a very narrow range. Now our eyes just see it as color. But technically, radio waves, microwaves, the infrared rays, all of those ultraviolet rays are all technically part of light. So that's the reason why plants, they can take light energy and they can use it to make food. We can't do that. It just makes us
I wish we could do
warm.
that.
That would be very nice and very convenient. Okay.
Doesn't the sun also give off electromagnetic rays, which also gives energy?
Now keep in mind, we don't really use that for energy like for us, but yes, it warms up the plant. That's the reason why they can use ultraviolet like spectrums to help measure the like temperatures, different types of the
It's
sun as well.
electromagnetic rays and what is it called? When, like it's just solar. It's like
Solar flares?
solar flares.
That's
it.
whenever you have basically the sun release more energy on one
Because
side.
the solar flares, I saw this thing like if there was solar flare big enough to hit Earth,
That'd be
and
bad.
we wouldn't not necessarily. I mean, it would just knock
If
out.
it
the-
hit
we-
the Earth-
If it got, no, I'm saying if it got close enough, it would knock out all electricity on Earth for like 4 days or something.
Depending on what happened, like for example, the sun is so far away, like whenever the sun starts to kick off light, it takes 8 hours for the sunlight to get to us. So depending on what happened, that yes, it would cause really bad things on Earth, like because the sun is so far away from us, which is a good thing because you don't want to be right up close to it.
So wait, if the sun burned out, we'd have 8 hours of light before it went dark.
Yes, basically,
Oh!
loosely. Depending on how, like,
But
if
the
the thing
sun-
like exploded, it'd be a little bit different. But yeah,
Yeah, if
basically,
the sun went out, then we'd die pretty much.
yeah, you have about 8 hours left, loosely.
Well, when you die, was really because that means it would turn into a.
Keep in mind, it is super far, so again, it takes 8 hours for something the speed of light to get to us. So most things are not faster, well, nothing's faster than the speed of light, so because, nope, that's part of the universal constant, is because light is as fast as we can, as something can move as far as we know right now, that's as fast as you can get. That's what come, light is a universal constant in the vacuum, it's always the 3.0 times 10, because that's as fast as it can get, basically, nothing can go faster than that. Alright, but no, we gotta get into this part. So, let's make a note that, talking about speed of light, so make a note for this equation, because little c, now remember in the last chapter in thermodynamics, little c met specific heat. Since we're talking about speed and light now, little c represents the speed of light. I know it's a little bit confusing, but they really use it because it's in a different branch of chemistry. So, make a note. So, what does the lambda stand for in this equation, Quentin? I'm sorry.
Wavelength.
Good job. And then what does the F stand for, Chris?
Velocity?
Not velocity, that's V.
Frequency.
Frequency. So speed of light equals the wavelength times frequency. So your book points out that the speed of light in a vacuum never varies. Doesn't matter how you measure it or when you measure it. It's always the same. And scientists know, that's weird. But it's part of the universal constant of the speed of light never, ever, 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 ever changes. All right. So with the electromagnetic spectrum, you can have larger waves, and then you can have really short waves. But if you have a longer wave and the speed of light never changes, if I have a long wave, what does that mean for the frequency then? Ethan. The speed of light is always the 3.0 times 10 to the 8 meters per second. And I have a long wavelength though. What do I have to balance it out?
More light.
Okay, not more length. So will the
Light.
frequency, sorry.
Said more light.
Okay, not more light, because if I have a long wavelength, will the frequency have to go up or go down if the speed of light is not changing?
Up. Down.
It'll go down because they're inversely proportional. So with the idea, if I have a really long wavelength, that means it's gonna take it a long time for one wave to go by. So it's one of those kind of like if you've ever sat at like a train, like crosswalk area in your car. If it's a long train, you're gonna be sitting there for a good 5-10 minutes, depending how many cars are on that thing. So that's the same idea. If it's a long wavelength, you're gonna be sitting there for a long time to have just one wavelength go by. It's gonna have a really short frequency because the idea of it's a number, so it's gonna be really low how many wavelengths go by in a second. Okay.
Isn't
Yeah.
UVC harmful to us?
Wait, say it one more time.
Isn't UVC harmful to us?
UVC, yep. So ultraviolet radiation, like type C, that's the one that's blocked by the ozone layer though.
Oh, it is?
Mhm.
I didn't know that.
Okay.
How condensed are the light waves that the sun gives off us? Are they super condensed? Are they like, would they far be stretched out like the waves?
It gives, I believe, for the sunlight, it gives infrared, ultraviolet, visible light. I think the sun gives parts of X-rays and microwaves as well. We just don't really remember this. I'm not sure if it gives the full-on radio waves or not. I haven't checked
No,
that.
I mean like see the wavelength of the one that's in the book, the one that's there. Is the waves of light that the sun gives off, like are they super condensed like you see on the right side, or like more like?
Okay, look in the middle part section. So you see like infrared, visible light, and ultraviolet. See those waves and their wavelengths? Okay. That's it. Yeah, so that's the light part. I'm not sure how far it goes in either direction, but they can actually measure it. This is one reason why whenever we have white light, we have it in that frequency. That's the light we can see. Wow, if it was, no, typically we compare it to frequency because that's easier for us to work with. If it's in a higher frequency where it has more energy, it starts getting into the ultraviolet light and X-ray light. Okay, can you see X-ray light?
No.
No, your eyeballs cannot see that. Your eyes are not basically tuned to that. So you can't see that type of light for it. So if it was just X-rays all around you, you wouldn't be able to see it because you can't see that particular light. It has to be in that particular frequency for your eyes to see it. Okay.
Is that what goes into the actual X-rays?
What?
X-ray is the light.
Mm-hmm.
Is that what they use for like X-rays?
That's it. So that's that's the reason why the lady typically leaves the room is because she can't get shot with the X-rays over and over and over and over again. That's how come the dentist or the nurse will leave you and you wonder, why are you leaving me right now? But it's because she can't be exposed to that over and over and over again. So that's how come she leaves the room. Now you get exposed to it once, twice, 3 times a year, maybe 4 or 5 times if you've had a really bad year, you gotta get X-rayed a bunch. But that's one of the reasons why, okay, she leaves because she can't get exposed to it over and over and over again. Okay.
2 things. Is the reason she can't get exposed to it because of the radiation?
Yeah, because she could develop like cancer and stuff if she gets too much.
And so, if you, I guess 2 more things.
Okay.
The X-rays, if you were around them enough, would your eyes eventually tune to that frequency of light?
Your eyes are just not designed for that.
You would go blind before?
I don't know if you would go blind, but your eyes just like, they're not programmed to notice it. And so because, that's part of the reason as to why color is amazing, is because your eyes, with your, you know what, okay, this is getting into biology, but does anyone remember what are the cells in your eyes and your retina to see light and to see in color?
Cones?
Rosin.
Look at me.
And so because of that, this is one reason why if you start to turn off the lights in a room, everything starts to go in like black and white. It's because there's not enough light for your cones to register the color anymore. Also come if the light starts to go down, you start seeing everything not as like muted colors, it starts to look more black and white.
Oh,
It's
yeah.
because your eyes don't have enough light to see it at that point anymore. There's not enough to
That-
trigger the cones.
Is that why they created TVs that much first?
It's just because they didn't have technology to record it and to basically capture the light and to write it down for your TVs to show. So everything was in black and white. Now, they had colors back then. It's not like everyone existed in a black and white world and all of a sudden, whoa, colors!
Yeah.
No, that's not what
I
happened.
used to think that was a little.
It's okay, that's a common misconception. You just kind of assume that as a little kid, and one of those, as you get older, you realize, oh, whoops, yeah, there's no things that happen. But yeah, there's nothing special about those frequencies for colors. Your eyes are just programmed to see that if it's that light bouncing off an object, like looking at my floor is obviously blue. But it's because the blue light is reflecting off of it, and that particular frequency tells my eyes that is blue color, or that is green color, or that, is brown color. And so because of that, it's just those frequencies, they tell your eyes what color's there. This is why if you have someone that's colorblind, that it's not the object themselves are changing, their eyes are messed up to where they can't see the proper colors for that frequency. It's still bouncing the light, it still works for everybody else, it's just their eyes aren't properly like programmed at that point to be able to see it. And you can wear glasses and stuff to like help correct it and
If
stuff,
you
and
were
that's
to
fine.
if you were to like say get shot with a gamma ray, would it like hurt you really, really bad? Or
So like gamma ray?
yeah.
Gamma ray is a type of radiation that they use to kill cancer cells. So now if you got shot with it, a small dose, like a small amount in like one spot of your body, you will probably be fine. But typically you don't get shot with one part of it. It's a bunch of it all at
Or
once.
if you get shot in the eye with one, would it blind you?
I would go with yes. I mean, a little bit, depending on where it hit, you might still be okay. But it's basically like a little bitty tiny laser that goes through you. So depending on where it hits at, yep, because it goes through your body. Gamma radiation is strong enough to go through you. It can go through, I forget how many inches. It basically kills the cells that it goes through though, because your cells aren't designed to have basically a little laser. What?
Maybe generate quick enough where you don't even see a hole.
Oh yeah, no. Gamma radiation is super tiny. Like, if you get one little thing of gamma radiation, it'll be super small. You should be fine. Even if it goes through your eye, you might still be okay unless it like struck like the exact wrong thing. You still might be. You'll probably still be fine. But again, you don't really get like one gamma ray. You get a bunch of them typically all at once. Probably not, because it would have to activate the exact nerve as it went through. But again, you typically don't get one gamma ray. You get a bunch of them all at once. And if you get a bunch of little holes all through your body at the same time, not even done. Alright. So again, this has to do with the electromagnetic spectrum. Again, it is fun talking about it with all the arrangement of all forms of electromagnetic radiation in order of frequency and wavelength. This is the electromagnetic spectrum. This is all of it. So you have electric power waves down here with that type of light, radio waves. That's the reason why your radio runs on electricity. That's the reason why if you get so far away from like a radio station, you can't hear it anymore, or it starts to get all garbly and staticky, is because you can't pick up that type of light signal anymore. Microwaves, this is one reason why on your microwave oven, how it works. So it means for microwaves is a type of wave. This is something to where your microwave uses it. This is why you don't put metal on the inside of a microwave whenever you're heating up something. Like
That's why mine exploded.
Let's say that. Yeah, that's why it's bad. We're talking about that in junior high too as well. As a side note, don't do that at all, ever. So this is one reason as to why that it causes bad things on the inside of the microwave. Infrared or infrared light, it's also some people say it, but infrared typically. Anyone know what type of light this is? We cannot see this, but some animals can.
Infrared light, like see where you can see infrared, or you can see heat structures.
That's it. So it's heat vision basically. So you have heat. If you go hunting and you have a and you have heat goggles or like a heat scope.
And you're pretty rich too, because that's
yeah, they're expensive. I was looking up prices for those things. Yeah,
$120.
they're more than that typically for a good one. At least the ones
A
I
good
was
one,
looking
yeah,
up.
they're expensive.
Yeah, they're super expensive. But yeah, that's the reason why we cannot see that. There's a couple of animals in particular. Anyone know what organ of the snake that can do that?
Start with a J.
Yep. No, you're thinking of the scent one. That's the Jacobson organ. This was just for heat. This was for vipers like rattlesnakes.
I got it. I don't remember, but I have a question.
That's good. Pit vipers, so yeah, it's the pit inside. So they can basically see and heat vision. So they can see the heat coming off the bat. So even if you're thinking, I'm gonna be super still, rattlesnake won't see me. No, rattlesnake knows you're there. Rattlesnakes doesn't actively hunt humans most times. So they will typically leave you alone if you leave them alone. Now if you go up and step on them, rattlesnake gonna get you.
Cottonmouth gonna chase you.
Sometimes, yeah, but a lot of cases, if you leave them alone, they will leave you because they can
Not
see.
cottonmouth, not-
Okay. Now, a lot of you, because you're so large, they will typically leave you alone. But again, if you go up and start messing with them, they will get aggressive. Okay. Yeah.
I don't know if I've asked you before, but like animals like cats and dogs, do they see black and white?
Dogs do. Whenever I was looking this up, for, I think for junior high or something a couple of weeks ago, that they think still that dogs that they see in black and white, cats, they think that they have better, vision for motion. Like, that's the reason why you don't know something until something moves typically. They think cats have a better version of that. So that's the reason why they can hunt smaller objects better than we can. They're not sure about their colors, at least the sites that I went to, but they think that they have better, like, motion sensation vision.
You mean like they can see like even like a small bug moving?
Yeah.
Or do you think, or you mean that they can see them like their muscles start moving before they even go anywhere?
Okay, that would be like seeing on the inside of their body. So this is one
Ultra
reason why
instinct. What you
a lot
talking
of
about?
our eyes, like humans, like if you're really still, humans have a tendency to overlook you or to not notice. One reason why, if you're hiding like in paintball or laser tag, if you're still, the person might not notice you. But once you start to move, your eyes will notice, oh, that's movement, and your eyes will latch onto it. They think that cat's eyes can do that better. That's the reason why if there's just a little bit of movement, that they'll notice it and notice, oh, someone's over there, and they can go catch it that way. So they think they have slightly better like motion and vision that way for it. So again, not quite with the idea of color. Again, different animals have different types of abilities. Like some insects, they can see beyond just what we see with the idea of visible light. They can see in the ultraviolet light. Now we can't see that either. But it's one of those where they can see it on the patterns. You can't see ultraviolet. That's not part of the human spectrum. But it's the idea they can see patterns even on flowers that we can't see. A lot of flowers have basically invisible patterns, kind of like a bullseye around it, helping direct insects towards the center of their flowers, towards the pollen and towards the nectar. And we don't even notice that. We just see, oh, pretty daisy, pretty flower. But insects can see different patterns that we can't see it. And then of course, X-rays and gamma rays. So you'll notice though that they are inverse or opposites with the idea of wavelength and frequency. You have a really long wavelength, you have a very short frequency. But the shorter the wavelength gets, the higher the frequency. Typically, the higher the frequency, the more energy a wave has as well. This is why if you get shot with radio waves, which radio waves are all around us right now, because there's radio stations, you're fine. It doesn't matter. Your body's okay. It can take it and it'll be fine. You get shot with a whole bunch of gamma rays, you're gonna die. So that's the reason why we associate frequency with energy. Alright, anyone have any questions about that? Okay.
What is gamma rays again?
Gamma rays, it's the type of radiation that has a lot of energy, and it basically, whenever it goes through you, it kills whatever cells that it goes through. Again, if you get one individual gamma ray, you'll probably be okay, but if it's a bit typically you don't.
Place a hole in.
What? Basically, it's a little bitty tiny hole that it makes. So if you get one itty bitty tiny hole, you're probably gonna be fine. But if you get a bunch of itty bitty tiny holes, not fine anymore. Okay, so just make a note of that. Anyone have any questions about this? With the electromagnetic spectrum, this is all of it all together. Alright, so the quantum theory of light. So working with light, scientists are saying, okay, well how does light work? What does it do this? It acts like it has BBs, or it acts like it has matter. This is why you can have shadows be cast. But it also moves in an up and down pattern with electromagnetic radiation. It moves like a wave. So what is it? So scientists, they wanted to explain it. And they eventually said, it's both. We give up. There's no other explanation for it. The book talks about Max Planck and Albert Einstein. It focuses more on Max Planck, since Max Planck did more with light in particular. So just make a note that it was technically both of them. But Max Planck and Albert Einstein, they said, okay, that light, it has principles of particles, where it acts like matter, and it also acts like a wave at the same time. So it's both. It's wave-particle duality of light. So make a note for that. So wave-particle duality is both parts. It acts like a wave, and it acts like matter at the same time. So it's both of them. They use this to kind of take this and turn it into the quantum theory of light. The quantum theory of light states that light consists of tiny bundles or packets of energy called a photon. You might remember that from biology. So you have little bitty packets of energy of light called photons. This is what moves through space, and this is what gives plants energy that they need to make glucose. So it's the photons that are in the light. But photons, they have matter, or they have energy, but they're also moving in space in that up and down, or that wave-like pattern for it. So your book points out it's kind of hard to wrap your head around a little bit, but scientists just know this is the best explanation we got. This seems like it's accurate, so this is the best explanation we got, even though it feels kind of trippy and kind of weird for it. So your book points out photons act like particles, but when traveling through space, photons act like a wave. Light is simply described as electromagnetic waves traveling as photons. That's the definition of light your book gives for it. It's a little bit weird, but it works. Alright, your book points out light must consist of whole numbers of photons. You can't have half a photon. You can't have 3/4 of a photon. You either have it or you don't all at once. Alright, your book gives you I'll give you the equation to figure it out as well. So according to the quantum theory, the energy, so E stands for energy field, so at least that's nice and that's convenient. So according to the quantum theory, the energy of a photon is directly proportional to its frequency. And like I was saying, the higher the frequency is, the more the energy is. So it's directly proportional to it. H is Planck's constant, so we named it after him because he worked with this. So Planck's constant, making up for him as well. So 6.63 times 10 to the negative 34, making up for that one. Alright, that's pretty much it for this section. Anyone have any questions about quantum theory of light, Max Planck, photons, light, the equation?
Do we need to know the value?
Yes. So 6.63 times 10 to the negative 34, that's Planck's constant. Alright, and let's see if we have questions about this. Alright, moving on, because light and electrons have very similar structure, so scientists started looking at light, trying to figure out, okay, how does this work? Now, what are the three parts of an atom? You're about to kind of go back and review a little bit. Alright.
Neutron, proton, electron.
Good job. Which one's on the outside of the nucleus, Ethan?
Electrons?
Good job. So, scientists said, okay, we have protons and neutrons in the center of the atom, and then we have electrons around it. So they were trying to work with light, and then while they're working with light, they started discovering weird things about colors, and noticed, this seems like it's related to energy or electrons. So they kind of discovered it in a roundabout way. So your book starts pointing out that whenever you're working with colors or light, you can separate white light into its colors. So anyone know what colors you get whenever you separate white light into the colors?
Isn't it like red,
Yellow.
blue, red, yellow, blue, purple?
Okay, that's 4 of them. There's 2 more.
Is it
Basically, we talked about this yesterday. Sometimes.
orange,
Yep.
green, and green?
Good job. So red, orange, yellow, green, blue, black. Basically, separate out into a rainbow. Anyone know how rainbows form? As a side note, I know this is not current.
Something with the rain or something?
That's a part of the rain.
It's the UV light saving up the moisture on the ground.
You're thinking of a different type. So if I see a rainbow in the sky, how does it come?
Is it like in the sky?
Mhm. Like if I see like a regular rainbow, it's like, oh, cool. How does that rainbow get up there?
Chromatic, like the chromatic lights that hit like the water at a certain space, but it goes away if you look at it at a certain angle too.
Yep, it's basically the light as it goes through raindrops typically, or moisture in the air, it's bending, or basically acting like a prism in the sky, so it's causing it to bend that way.
Since I've seen a rainbow.
What?
It's been like a year since I've seen a rainbow.
I think I saw one, 3 months ago, Lucy. Like it was a faint one, but it's one of those, hey, and then you
At my uncle's funeral, there was this guy got up and he said that my uncle was kind of like a rainbow into everyone's life, and like a double rainbow because like whoa, it's crazy, you know, the video.
Oh yeah, I've seen it.
Yeah, and then we went outside after the funeral was over, and there was a double rainbow.
Oh, that's
And
cool.
now that's kind of like whenever we see a rainbow, that's what we think about, and we had like shirts made with the double rainbow on it.
Oh, that's cool. That's always nice when stuff like that happens. Alright, so showing, okay, if you use regular light, that whenever you shoot it through a prism, you get a continuous spectrum, or you get basically a rainbow. So scientists are knowing, okay, if you use regular light or sunlight, so white light basically, so if you were to use it with the fluorescent bulbs, you'll get it. Now, because these bulbs are so large, it's hard to work with them. But yeah, if you use a regular light bulb, you shoot it through this device. This is a spectrometer, as a side note, so note the device as well. Basically, if you shoot it through this, you magnify it, and then shoot it through a prism, you're going to get the continuous spectrum, or get a rainbow. Alright, yes.
Is that what they do on computers and stuff?
What do you mean?
To produce color?
Okay, that's a little bit different. They use, now do you remember from physical science, I know this is like 3 years ago, but do you remember with pixels, what is, like, how they make colors on the inside of TVs and computers for pixels? But they use basically those 3 major colors, and they can make on your screens all the different colors from it. Now that's early versions of computers and TVs. This is why early TVs were in black and white. Now today they use more of LCDs or plasma screens to help show it, but it's not quite the same way that they're using it for this one. So this is an example of a continuous spectrum. So whenever they're using it though, they can use a spectroscope or use a better version of this if they're using it to get a line spectrum, or basically split it up into colors. So that's what this one's showing you. That if they want to know again, they're using a high voltage discharge tube, not still white light, but they're using basically a different version to try to measure it out a little bit differently. They shoot it through, and instead of getting a continuous spectrum, they get a line spectrum, or it's basically separated into its component colors. This is one reason as to how come people wonder is indigo its own color, is because it does have its own frequency. So they're not sure, or do they consider it an in-between one? So
It
scientists.
has its own frequency. see it as color.
But every color has its own frequency.
Yeah, well, some of them, we'll talk about some of them light, and some of them are blurs together, to where if you, because your eyes basically mix the colors together, we'll watch this with line spectrums later if you still have time today. But it's one of those where your eyes don't see two different colors, they just see it as one color. Like yellow can do this as well, to where yellow has its own frequency, but you can also make yellow by blending colors of light together. And so it's one of the reasons why scientists wonder, okay, is this an actual color, or is it just a blurring color? So, to make it up though, a spectrometer, a spectrometer, that can be used in a laboratory to separate colors even further and study them in detail. A spectroscope, that's whenever you have a prism separate the light into its component wavelengths. So, these are types of spectrometers, but they're more specific ones. So, a spectroscope. Make it up for that one. I think that's everything for this part. Flip over to the next page, page 98. That they started working with different elements, and they started noticing that, if you light elements on fire, they glow different colors. But then also, they were noticing that whenever you put them through a device like this to get the line spectrum, that they have different line spectrums. They have different kind of fingerprints to help identify them. So passing an electric current through a gas under low pressure produces the line spectrum, but it's not the same for all of them. So scientists noticed, not only do they glow different colors whenever you light them on fire. Like, anyone remember from the previous lab what color sodium glows? You guys remember the guy who like scraped his palm and stuck it in what?
Blue.
Not
Oh
blue.
yeah, I remember that.
What color?
When he did that.
Yeah, he did his palm
it was
for
like
sodium.
clear, wasn't it?
Pink.
Not pink.
I thought it was like clear, wasn't
It showed up on the video as like this weird kind of, well, he described it as one color and it looked slightly different because of the camera trying to photograph it. Does anyone remember?
That's blue. I thought it was blue.
Not blue. Alright, it was, so sodium is orange or like yellowish color for it. So that's what sodium is. You might be thinking of a different substance from it. But that's what sodium is. So for the line spectrum, they were noticing that, okay, whenever they ran hydrogen through it, they noticed that hydrogen had a mathematical actual ratio for it. So for this one, hydrogen's down here, so they noticed that there was a mathematical equation that they could use to figure out the line spectrum. It doesn't work out for all of them, just for hydrogen, but it allowed scientists to go, that's weird. If there's a mathematical equation we can use to map out the lines and that we really see, do all of them do that? So it started making scientists more and more curious over, why is it doing this? How is it doing this? What's going on with this? And so it made scientists more and more curious about it. Alright, I want to go ahead and watch the video about the line spectrum just because it is cool and it is interesting and it helps demonstrate this. Alright, either go with the light. It's not a full-on lab, so you don't have to get your lab book for it. Alright. Jamie, as a side note, you probably want to fast forward this because I don't think it's going to show up well. I'm sorry. If you want the YouTube link, I can email it to you later on, but it's not going to show up well. So if you want to fast forward this part of the video, that is fine.
How was the video?
Like 6 minutes. He's doing a good job demonstrating line spectrums and then also with the device.
This is one of our funnest demonstrations to show atomic spectra. I'm going to show the spectrum of an incandescent bulb, which is continuous. And then I'm going to show the spectra of 4 different elements: mercury, nitrogen, neon, and especially hydrogen. Hydrogen will be important in the labs and in many other applications. So to show a spectrum, what we use is called a diffraction grating. This looks like a piece of clear plastic, but it's not. It is actually a piece of clear plastic on which an image has been inscribed with dark line, clear line, dark line, clear line, with about 10 to 13,000 lines per inch. So it's called a grating, just like a street grate. It has lines through it, and this allows you to resolve the spectrum of a source of light in the same way that a prism will resolve a spectrum. So what I'm going to do is to place this diffraction grating in front of a camera and show you the view of this continuous source with it.
Okay, so like I mentioned earlier, that our eyes, we only see this as white light, but all of these colors together are part of white light. So your eyes just see all of them blended up together as white, But if you separate them out, you'll get all the other colors. Now he's looking at a screen whenever he gestures. As a side note, if he's slightly off, that's the reason why.
Diffraction grating in place. And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to the left, you'll see a rainbow spectrum that shows what wavelengths are present in this. You'll see, as you look on the right side, violet through all the colors of the spectrum, all the way through red. So that's a continuous spectrum. We'll try next to look at a discrete spectrum of mercury. Now what this is it's a discharge tube. It has mercury in it, and what I'll do is energize this tube, apply a voltage to the tube, and that causes the gas in it to emit spectral lines according to the spectrum of the element that we're using, in this case mercury. So I'm going to locate this, its proper spot, turn off the continuous spectrum. So this is a mercury spectrum without the diffraction grating. I'm going to get it in focus here. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place. And what you see in this case are...
So again, these colors are on the inside of it, so he's separating out the colors that are giving off from it, but your eyes only interpret it as one color. Your eye blurs them together, so you only get one color coming off an object.
A green line and a blue line predominantly in this mercury spectrum. Next we will try a nitrogen spectrum. I'm using this fur to prevent burning flesh.
It's hot.
So this is nitrogen spectrum.
That's cool.
And with the diffraction grating in place, we see a number of lines present, some red, orange, yellow, green, and a violet turquoise-ish colored line. That's nitrogen. Two more. This is neon.
That's really cool.
There's a beautiful orange look to it, and when the diffraction grating is in place, you see a large number of red and orange lines.
So question, Chris, I just can tell.
This is exactly what's used for neon lights. The original neon light was made out of neon like this. There are other gases that are used to form signs, but the neon was really where it started off. It has a beautiful, bright, reddish orange spectrum. So this is hydrogen. It has a reddish cast to it, and when the diffraction grating is in place, you'll see three lines. The farthest from the central image is a red line. That's the hydrogen alpha line, and it is very important in star images. A lot of nebula in the sky have hydrogen alpha line as one of their prominent spectral lines. Then there's a turquoise colored line, greenish blue is the hydrogen beta line, both from the Balmer series, and we'll talk about those, or have talked about those in class. And then finally, the hydrogen gamma line is a violet line, is generally considered to be the one that's those three lines are visible in the hydrogen spectrum. Those lines are associated with transitions of the electron in the hydrogen atom from a higher state to a lower state. In this case, the second energy level is the final state, and then higher energy levels, it starts from a higher level and goes down to the second energy level to get the Balmer spectrum. That is continuous and emission spectrum.
Yeah, he got a little bit technical towards the end, but he did a good job explaining the different parts, looking at how different elements, not only do they glow colors whenever you heat them up, but you can actually separate them out into those line spectrums.
Where does he teach at?
I think it said at the start of the video, but
High school or college?
college. Alright, so anyone have any questions though about the line spectrum? Alright, so the Bohr model,
A question and
okay,
so if you have the lights on and
okay,
everything,
yeah.
and then you turn the lights off and you still see color still kind of,
Mm.
and then you cut out all lights from everywhere, it'd
Right.
be pitch black, like you wouldn't see any color.
Yes.
Right? That's how light works.
Yep, so like for example, sorry James, it's gonna be brief for a minute. So, like if you turn up the light in here, you'll notice that the colors that they fade a little bit. Now you can still make out colors, but it doesn't seem like that the colors are as bright. That's because there's less energy or photons hitting your cones. Now, your rods, they are more attuned to just black and white. So that's how come whenever it gets darker, you can still make out shapes and textures, but you can't make out colors as much because there's not enough light for your cones to be activated in and of itself. That's how come you can still tell where stuff is in the room. You might not can see the colors as well, but you can still make out of where people are, where desks are, and so that's how come you can still see in the room, just not as well in colors. Okay.
It's not possible to get completely dark as it possibly can be on Earth, is it?
If you go to a cave, how many of you have been spelunking before? Alright, you notice how, they've ever turned off the lights in the cave before? It's like oppressively dark, like you can feel
Oh
like
my
the darkness
goodness.
is pressing in
Yeah.
on you. That's because there's no light down there. It's typically, if you're going like deep spelunking, because you're so many feet under the ground that there's no light down. This is why if you had explorers, they would have to bring their own light with them. Occasionally, you might find something that is bioluminescent, that makes their own light, but typically down there's no sunlight to get down there.
If there was no sun, there was no stars, there was nothing in this entire universe that emitted light,
Dead.
it would still be, well, yeah, say we were somehow alive, it would be just as dark as it was down in the cave as it would in space.
Ignoring the animals that are bioluminescent, like fireflies,
Mhm.
yes. And so we can use electricity to generate and to make light. So if you're people that like move fast enough to like turn on the lights, okay, you could still carry on light that way, but you're using electricity at that point. So you'd have to use a generator. But at that point, Earth will not be around because
It'll
that's
just be a
our
solid block of rock.
Yeah,
yeah, we
lots
get
of
sunlight
lights.
or energy, so if we would cut off our heat source, plants would all die, seasons would
We'd
stop.
freeze.
You wouldn't be here to see the end of the Earth.
Yeah, you'd be dead. You'd be dead very quickly.
It'd be
And so
dead.
that's my reason as to how come God gave us the sun,
There would
to
be
help
no
us
end of the
give us
earth.
our energy, to give us weather, to give us food for plants. So yeah, there's a lot of valuable properties with light, not just being able to see. No, being able to see is nice. It's very nice.
But hell is still gonna be darker than it was in the cave.
Mhm.
How is that possible?
Well, keep in mind, hell is a spiritual place, so there's a lot of properties of hell that don't exist on Earth. Like the idea of constantly falling, you don't really have that because your
You're
body will.
constantly falling in hell,
Because it feels like you're constantly falling in hell.
in your own, like, put you on fire.
Yep.
And
So
it's completely dark.
Yep.
Fire emits light though.
Well, keep in mind,
And all of it.
there is a theory that if you get fire so hot, basically, I forget how they explain it, but it turns black basically, like it's
Yeah,
black
I used to
fire.
also
I
read
forget what theory that is, but it's like beyond white light, like I forget if it's something where like it lights light on fire or something like that, like it combusts so much, but it's called
Dang.
black fire. I forget what they call, I forget like what's the theory for it, but there is a theory where it say like it's so hot that it goes beyond where
Over
not even white.
2000, over 2000.
It's a lot. I forget what it's more theoretical than like actual practice because again, stars emit light
Because
and
how
they're
high is the
white
sun?
light.
How high is the sun?
Ooh, it's a lot.
Like over 10,000?
I would say loosely yes, but it's been a while since I looked at the exact number in Fahrenheit.
The core is hotter than the outside, isn't it?
What?
The core is hotter than the outside, isn't it?
That's the same with Earth. The core of Earth is pretty much
Oh,
hot.
yeah.
Yeah, they think that it's like molten iron something on the inside of it. But again, that's part of the reason why now again God made it as a punishment place for the devil and his demons. We were not ever supposed to go there, but since God has to
I have a
punish all sin equally, God can't say, devil, because you sinned, you went here, humans, because you sinned, you went here. Okay, God has to be fair and consistent. So that's the reason why you end up in hell if you're not saved because you sinned. Okay.
A quick question. Demons, like you said, he made a punishment place for them. Do they feel like that they do that?
Yeah, no, it affects them
They go
too.
through pain too?
Yeah, it affects them too. So, I mean,
So they
it's all
torture people.
equal on that side of
And
it.
how do
Or-
they?
And you never get used to it, sorry, you never get used to the pain,
Mhm.
never.
No, it goes on for, and honestly, we can't get into this a whole lot, but I think the scariest part of hell is the fact that it never, ever, 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 ever ends.
Oh, that's the part of
So
it.
that's the trippy part of it. It's one of those, okay, if it lasted for 100 million gazillion years, well, at least it would end. Like it would be a bummer
That's
all
the-
through that. But it's one of those, it never, ever, 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 ever stops.
That's the idea of salvation, you know what that scares me is, I don't wanna be just somewhere forever, like I wanna
Well,
just
keep in
be
mind that you'll be with God, and God's going to make us a new heaven and a new earth. So, plus, since God can like recreate stuff, that we can always be discovering or learning or doing something productive or doing something fun. So it's not like you're going to be bored out of your mind. God has so much variety, and again, it is kind of weird to think about. Okay, it's gonna last forever.
If I wanted to in heaven, could I sleep forever?
That sounds like something you'd have to ask God whenever you get there.
Hey God, I wanna go to sleep forever.
I mean, because it doesn't really talk about a whole
Like that
lot.
sounds like heaven to me, like I'm not even trying to be funny, that legit sounds great to me.
I mean, it is supposed to be restful. We get to eat in heaven. At least
can't
there's
wait.
references
It
to
better
food
be
in
good.
heaven. So I mean, that would be nice.
I'm about to chow down.
So again, if you have to go somewhere for eternity, because you have to go somewhere. So it's one of those. One of them is definitely way better than the alternatives. Even though it is a little trippy thing about it's gonna be doing this for forever.
About to be on Mars
Okay,
600
you have to go somewhere forever. So because of that, you want to make sure you end up in heaven and not hell.
I'm
All right, definitely the better alternative.
I'm about, when I get to heaven, I'm about to be my 600 pound life heaven edition, if I can eat whatever I want, whenever I want.
That sounds like you have to just ask God and figure out whenever we get to heaven how all of that works.
Do
All right.
I have to work out to lose weight?
We have to go. Alright, so look at the Bohr model of the atom. So your book points out that okay, these early models of the atom weren't really working out with what they were discovering with light in particular and what they're discovering with the hydrogen atom. Alright, your book references the two models we've already talked about. So J.J. Thomson, anyone remember what that model was?
The
Electro spectrum, back spectrum.
This is like way back in chapter 2.
What'd you ask? I thought you
J.J.
said-
Thompson, what was his model of the atom?
Oh, that was the pulmonary.
Yep.
No, the plumber.
Yep, the Plum pudding model. So it was basically, he thought that it was a giant, like, positive sphere with electrons embedded throughout of it, and scientists said, okay, no, that's not right. So, and then you had Ernest Rutherford. Alright, what model did he come up with?
Rutherford.
The tinfoil, the foil one.
Yep, that's a little later. So, he
The
came
oil
up
drop,
with,
the oil drop one?
that's Millikan. So, Rutherford came up with the planetary model with the idea of, okay, you have the nucleus. This is the one that people draw typically, and you have all of the electrons going around it.
The Big Bang Theory.
Nope, not quite. But it's the idea of,
The
okay,
show?
that they're all
Fuzzy
going
over.
around it. So, they started noticing, okay, if that's right, that's not gonna work either. But I'm just about out of time to talk about the reasons why it doesn't work later. Alright, so page 98 for homework. I'll probably make it a little bit farther. Pages 98 to 102. 98 to 102. Answer on page 105. Alright,
Hold on.
answer on page 105. Alright, you should be able to go through 1 through 5 on page 105, 1 through 5. 1 through 5.
That's all the homework.
I take it back, you can't do number 2. So 1, 3, 4, and 5. You can skip 2. So on page 105, 1, 3, 4, and 5. You can skip 2 because we're not quite to that one yet.
Take it back over.
Yep, really quick. Alright, what do you call the tiny bundles or packets of light?
Atom. No,
Nope.
photon.
Photons, good job. So if I have a higher frequency, will I have more energy or less energy?